Thank you. Yeah. So thank you, Ivan, for the invitation to this very interesting conference. It's a wonderful place. I would like to thank all of the people around you who made this a pleasant event. So I've been told that the audience was very diverse. Many fields are represented. So I decided to make a presentation of something which is a bit more than my usual research activities, which is a kind of almost at the frontier between physics and biology, even medicine, oncology, as you will see. But I have to be very, very humble. I mean, that's not how we say. I'm a physicist, so I will really do physics, but putting real numbers, measuring temperatures in degrees centigrade, time scales in seconds, and trying to make a very simple model like we do in physics, usually assuming symmetries in such a way that the equations can be solved in some way. And but still, I hope that this can have something to do which is relevant in therapy, in oncology, to a typical domain which is called thermal ablation, which we'll describe just in a moment. What I want to say also is that my knowledge is that in biology and in medicine is almost zero. So I will make a very, very basic introduction of the biological processes before going to the physical approach. And unfortunately, cancer is something which is a very sensitive problem. Unfortunately, most of us know people who have or had cancer. So I hope that my description of thermal ablation will not hurt anyone and to understand. I apologize, of course, if I'm making a presentation which is not subtle enough. So, okay. The work which I will present was done in collaboration with Andy Manapane, who is a PhD student, and Sébastien Fubron, with a colleague of mine in the University of Nancy. And essentially, this is a description of the role played of the heat transfer in the vicinity of some topological defects which are present in biological tissues and which play an important role in the phase, the aggressive phase of cancers, which is called the metastatic cascade. These topological defects are present in many, many different fields in physics, of course, not only in physics. And for me, that was quite a surprise to see that they are also very important in biology. So that's basically the plan of the talk. I will start with showing you that things that biologists know since a long time, that topological defects can be very relevant in biological tissues. Then I will explain at a very basic level the role that they can play in the proliferation of cancer metastases in the body. So this is a basis of our study, our further study, but I'm not sure that this is something which is very well addressed in the literature. Basically, I know only 2 papers in the literature where we discuss about this, but that's interesting enough to ask the questions I will try to show you. Then I will make the brief description of what is called thermal ablation in oncology. And eventually, I will speak about physics and the modelization that we do. This is, as I said, a super simplified model, very, very basic one, of heat transfer in the vicinity of these topological defects in different types of tissue in the body. Okay. So first, the presence of topological defects in biological tissues. Here there are illustrations in some tissues which are called epithelium or mesothelium, which is one special type of epithelium. These are the tissues which are envelopes of the organs in the living organisms. And the cells usually something which is far from the sphere. These are elongated cells, and that looks, of course, like nematics. So the sizes can be very big, I mean, from 10 to 30 or 20 to 40 micrometers. But you can see on the phase contrast images, there are there. So these are papers from 2017 and here 2021. So, for example, on the left part, you can see it on some phase contrast image where you see the cells. On the right part there, there is a kind of nematics, we can put just and superimpose the direction, the main direction of the cells, and there that looks like what we would in physics call topological defects of charge plus minus 1/2. So in this context, they call it the comet defect for obvious reasons, and this one the trefoil defect. So this is in epithelium, and this is in mesothelium. In the case of the ovarian cancer, which will be the one for which are larger number of results in the literature. Okay, so we can see very nice of these defects, the minus 1/2 and the plus 1/2 charge. Okay, these are different types of images, and I will refer very often to these two, and the comet defect and the trefoil defect, and the core is indicated in red there and in blue on this second image. So basically, these ones will be the most important thing, what I will say later. Okay, so as I said, that will play a role in during the metastatic phase of the cancer propagation. So here is something which I borrowed from the literature in medicine. The way the metastatic phase happens usually is in several steps, and so you have imagine that you have somewhere a primary tumor, a cancer tumor, which is there. First of all, this tumor can leave the organ where it was born, I would say. This is a mechanism called, I think, extrusion, when these cancer cells can leave and go through the membrane. Then they can enter either the blood vessels or the lymphatic vessels. There is another mechanism which is called intravasion when they enter there. And of course, they can go to different places in the body, and at some place leave the vessels, either blood or lymphatic again. And this is called extravasion, and there you have some certain number of cancer cells, which will be called later the cancer spheroids. And these can play the role of seeds for further metastasis. Okay, so what is the role of the topological defect in this mechanism? Again, I refer to the paper which is from 2021. So here we have two types of defects. Again, the comet on the top row. The second row will be for the trefoil, but I will essentially comment the first one. So this is again the phase, the contrast image with the core of the plus 1/2 effect, which is there. And what is interesting is the right panel there. So this is a panel where they are able to measure. So in the organism, there are motions of cells, and this image is able to measure the velocity of the cells. So they have an orientation of the axis, which is the interesting one is the x-axis, which is horizontal and oriented to the right in this figure. And the core is in the middle there, okay? And there is a left panel and a right panel. And the red part are basically the places where the component of the velocity is positive, and the blue parts, the component of the velocity along the x-axis is negative. So what it means is that the left part is mainly going in the right direction, and the right part is mainly going in the left direction, which is in the direction of the core of the defect. So there is a kind of drift of the cells, and this is what can play a role of trapping then the spheroid cancers, which will be attracted by the core of the defect. So that is measured there. There is a control sample, which is the image of the velocity when this is part of the core of the defect somewhere far away, and basically the x component of the velocity is 0. And the left panel has a positive and the right panel a negative. This is what I discussed with this color image there. In the case of the trefoil defect, it's a bit more difficult. I mean, there are basically 3 legs for the defect. And so the situation is different when you're on the leg or out of the leg. So I will not discuss this a lot, but basically, if the cells which are in the legs are expelled from the core, and the cells which are in between are attracted to the leg. So this is essentially due to some stresses, constraints, mechanical effects, and there is more space in the core, etc. So there are probably many difficult physical processes. Yes.
So just a big question, this is a two-dimensional layer, and you're not talking about spheroids here, for example.
Yeah, okay, they call it spheroids, and okay. I don't know what is the size, what is the thickness of this tissue. I mean, of course there is the thickness of the epithelium. This is in the mesothelium of the ovarian cancer. So but you are right. This is probably not a single cell, of course. Yeah, because that's a cross section. Yeah. Thank you. Okay, so the first probably the first indication is that these comet defects can play the role to trapping the spheroids, these cancerous spheroids. So then the authors of the same paper, they were making in vitro experiments incorporating these cancerous spheroids and looking at what they call the clearance rate. So the clearance is basically in the normal life of the cells. I mean, if there are some dead cells, cells of course cannot live forever, and when they die, they have to be removed from the tissues. So this is what they call the clearance, and there is a given rate which is the inverse of the time, and the higher the clearance rate, the more efficient this mechanism to be getting rid of the impurities, I would say, the more efficient it is. So you see on of course there this, no, sorry. There, this is just a description of what they do. They try to put the red part is supposed to be a cancer spheroid, and they try to image that this is basically a sketch which makes sense. So on the left, this is again the phase image which shows the comet defect. On the right, with some other imaging process, so the black dot in the middle is the position of the core, but there is nothing visible on this. And on the center image, they just visualize these cancer cells. There are markers to see them, and when they superimpose, really they find that this cancer spheroid is at the core of the defect. And on the right panel, they have compared different kinds of cancer. So of course we know that for even each organ, there are many different cancers, of course. So I don't know the difference between these, but there are the names of these different types of cancers. And what they observe is basically that the clearance rate is very strongly suppressed when the cancer spheroid is at the center, at the core of the defect, and the control there is again far away from the defect. Okay, so not only these spheroids are trapped, but also they can survive longer, I would say, when they are located at the center of these comet defects. And the same would be true for trefoil defects in the case of this clearance rate. So that's the basic assumption that we'll do for the rest. So as I said, I'm not aware of many papers on this. Okay, so this is probably very basic introduction, and that's for sure not the only scenario, of course. So yeah,
I'll make a question. Is it understood why these cells actually have a pneumatic character? I could imagine cells having many shapes and having them be elongated and pneumatic-like is just one possibility.
Yeah.
Why is that?
No, that's in the case of the epithelium, which is not all cells in the body have the so that's a common description for epithelium.
I agree, and I just wondered why nature would choose that, given you have lipid bilayers, and you think it would be confluent, but why would they be elongated?
So that I cannot say, I'm sorry. Okay, so I will now speak a bit about thermal ablation. So, of thermotherapies.
Yeah, I'm following up this question. So it's typical of epithelium, as you said. Is there any other parts of the body where we can find these elliptical shapes?
Epithelium is everywhere. This is the envelope of all the organs in and basically to separate an interior from an exterior with a given functionality.
Okay, so it's typical of the EPT.
Yeah.
Okay, thank you. Sorry.
And just maybe to follow one more time on the
Yeah.
same question, I mean, could we interpret some of these defects, like defects in hexatic ordering, for example?
Yes. I don't. They only mention these defects plus 1/2 and minus 1/2 and nothing else. I imagine that others could be possible.
It'd be easy to do a 5-7 construction in this cell and look and see if there's some kind of evidence.
There are probably some also energy balance, and these are the most common. And I've not seen others. Yeah. So speaking about now thermotherapies in oncology, so this is an excerpt of the thesis of Antimanapani, which I mentioned before. So for example, this comes back to, if we really speak about a scientific approach to the effect of thermal effects on the body, there is an example which I find very funny. So in the beginning of the 20th century, a medical doctor which was called Julius Wagner Lorraine, I don't know how to pronounce it correctly, and I did not know this person, but he got the Nobel Prize because he was able to propose a therapy for people having syphilis just by infecting them by malaria. And because of malaria, they got, of course, fever for certain days, or I don't know, and that was enough to kill the bacteria of syphilis. So that maybe that's known. I don't know. Yeah, that's known.
Yeah, but then they were killed by
Yes.
Well, if you think about
Okay, so that was a temporary curing. Yeah. Okay.
their temperatures went up.
Yeah. But I mean, that's if he got the Nobel Prize, that's something. I imagine.
Yeah, I think many don't prizes.
Okay, so that's a funny example, but there are many of these. So in the context we are speaking about, this is thermal ablation. So on the right, this is kind of artistic picture. I mean, the idea is basically to try to kill the cells, the cancer cells, the metastases, by heating them. Of course, what you want is to heat the cells, the unwanted cells, but you want to keep the healthy tissue around protected. Okay, so better than surgery because this is less invasive. There is this thermal ablation, which consists in putting a needle in. Imagine that the red part here is the cells, the cancer cells that you want to kill. You insert a needle there, very thin needle, and then using radio frequencies or waves or microwaves or different types of protocols, you can heat in the neighborhood of the needle. Of course, it needs you have to know where to put the needle. So this is done under imaging. There are many processes by which the cell can die. Okay, apoptosis, necrosis. So okay, biology they have only nomenclature to speak about that. You can, I mean, when a cell dies, doesn't mean that it burns necessarily. You just need to break, for example, the energy production in the cell or something like this. So the left panel there describes, which is taken from a paper in a journal speaking about cancer, describes a lot of different protocols which lead to the death of the cells. And this is a kind of artistic view, and you imagine that you have the needle coming and then like an umbrella, and then you're able just to hit the thing, keeping all the surrounding healthy. Okay, so which is clearly something which is challenging. On this image, we show something which is more realistic, but imagine that there is a tumor there. Under imaging, you can see where to put the needle, and then with radio frequency or something, you can burn. And the problem is to burn the whole tumor and to leave around, as I said, healthy. So,
Sorry, the imaging here is ultrasound?
yes, I think it's ecographic. So now I will go to something that Ivan mentioned yesterday. In the case of light propagation and in the presence of topological defects, he has shown that we can use effective geometries. Looking at the defects from far away, you can you can write an effective geometry with, I mean, people from Brazil, you mentioned, I think, Moraes and Satiro, for example, they have shown the expression of the metric of the present of various topological defects, but among them, m equal plus 1/2 or minus 1/2 that we will discuss later. So what we're interested in, this is essentially the spatial part of this metric. And that was done in this paper by these colleagues from Brazil in the context of cosmic strings, as you mentioned, that was a 4-dimensional space-time. Here we're interested in the space part of this. So, of course, these functions A, B, and C would be one if that would be just ordinary Euclidean metric in the cylindrical coordinates there, but they are something, of course, more complicated there. And we know how to write how to modify the heat equation in this context. Essentially, there are, of course, subtleties, but essentially by replacing the Laplacian by the Laplace-Beltrami operator, where all the components of the metric tensor appear, and that's what is given there. So basically what we will do is to modelize the heat equation in the presence of the metric induced by these topological defects. So that's just something which has nothing to do with what I said up to now, but there was no, I noticed yesterday that there was no chirality at all. There are topological defects, but no chirality in what I was saying. But I just wanted to show you that in a different context, we also played with different types of metrics. And if you have a topological defect, which is a screw dislocation, in the screw dislocation, you can look at the heat flux, the heat transfer, and we can see very clearly that the shape of the screw of the helix can be represented there. So that's a funny thing also, because you can induce an angular momentum, make something like a bit like Einstein-Lehas experiment, but with heat. But, okay, so that's just to put something with chirality somewhere, and I leave it, and I come back to the topological defects, but no chirality. Okay, so the first thing I said was to take into account the effect of the non-Euclidean metric. This is the part which is written in blue there. But on the top of that, in the body, of course, this is not just matter, ordinary matter, I would say. And one of the first equations proposed in biology to describe the heat propagation in the body, in the case of the muscles, in fact, was done in I think it was 1948, in the end of the 40s, by Penz, and he just added to the heat equation some terms. Here, this is a convection term which comes from the blood. Yes, the effect of the blood arriving in the organ, and there can be a metabolic term which we will neglect there because we will act with application of heat somewhere. So basically, you have an equation where you have here the parameters, which are density and the specific heat of the tissue. You have here the density and specific heat of the blood in the tissue, and here a term which is omega, which is called the perfusion, which is essentially the rate at which the blood arrives. All these parameters depend in which tissue you are studying this, different in the ovary or liver or skin or whatever. So, I'm noticing that time is going, so I have to go fast. But anyway, we will simulate this equation together with the blue terms and the red terms. And in what follows, I will show you these are numbers which we can find in the literature. So we found these numbers for prostate, skin, and liver. We did not find them for ovaries, unfortunately. And I will show some simulations corresponding to only the presence of the defect. This is written with some coordinates which are in such a way that this is without dimensions. Only the defect, only the Penz equation, the bioheat equation, or both of them, which is supposed to be what is interesting in the context of thermal ablation. So you can see this in the case of the liver, for example. The defect, the heat is applied at the center of the defect. And you see the propagation of the heat. I don't write the scale of temperature, but you will see later this. If it is only the Penz without the defect, the Penz terms, we have something which is symmetric, okay? And not spherical, it's symmetrical symmetric there. And when we have both of them, we have the third row. Okay, the question is to know when do the cells die, and that's another problem. And of course, that depends on the time exposed to a given amount of temperature. So people in medicine know that, for example, if you apply a temperature of 43 degrees during 15 minutes, basically 1000 seconds, cells die. But if it is 60 seconds, it's basically instantaneous, 1 second more. So there is, of course, a balance between the temperature and, of course, the duration, the exposition to the heat. And so what I want to show is basically this type of surfaces. We have the two parameters which I mentioned on the equation before. There is the bio parameter there, and there is a time scale which is there. So all the parameters, depending on the tissue and on the blood, are entering these two parameters. And I'm showing some curves there, some surfaces in this plane. And on these surfaces, of course, when it is red, it is hot. When it is blue, it is cold. And the question is, what are the tissues which are in the white part? So basically, on the vertical axis, you have the percentage of the area which has been burned, which is gray in this snapshots. See, so if it is there, it is not hot enough. Imagine that I have taken an example where the tumor is supposed to be the half of the radius, okay, which is there. So here it is too small. Here it is probably too much, and you have to be in between. So if I show the examples of, for example, heating at 49 degrees during 100 seconds. In this plane, so here it is a projection, it's easier to see, still bio number in terms of tau. I see that, for example, everything, skin or prostate or liver, are on the blue part of the space, which means that I have not heated enough, okay? So clearly, these numbers would not be correct to be efficient for these tissues. If I'm doing this longer, that's still not enough. But I can change the temperature also. I can go, for example, to 55 degrees centigrade during 20 seconds. And I see that now prostate seems to be okay. It seems to be, now again, I mean, I don't mean the model is too simple to say that the numbers which I give are correct. I'm just trying to say that it can be relevant, okay? I don't take this as something true. I don't want to meet an oncologist and tell him, in the case of prostate, you just put 55 degrees during 20 seconds. Of course, never, that's too primitive for the moment. But still, it shows that there are some evidences which maybe make sense. So that would be okay for prostate there, but not for skin. And if I go to something which is higher, 75 degrees during 20 seconds now, it's too much for prostate and liver, for example, but it seems to be enough for skin. So the difference in the location of these points, these are just the biophysical parameters. Okay. So maybe I will skip these things, these are different protocols for heating, which I will skip this, and maybe to go to the conclusions. As I said, this is an oversimplified, extremely simplified model, and there are some obvious modifications that we can make, which will require, of course, different types of numerical resolution of the problem. But one of the few things which I can mention, sorry, okay, still visible. I have used a very simple criterion to decide when the cells die. I had just 2 points. Basically, I know that at 43 degrees, we need 1000 seconds, and at 60 degrees, it's almost instantaneous, okay? Locally, where the cell is. So we need to have something, of course, more reliable than this. And in medicine, people have studied a bit this type of things, and they propose different kind of scenarios. We also have to find different protocols, maybe heating on, off, that was what I have not shown at the end, maybe a better protocol also. The most important thing is probably the fact that I have used there, all the simulations were made with biophysical parameters which were constant. Clearly, this cannot be true. I mean, when we are burned, the body brings a lot of blood, and there is a modification of the diameter, etc., to just to avoid the burning back of the area. So that's very clear that these parameters should depend on the temperature, which is locally applied. So that's something which needs more work, and also bibliography, of course. This is not something easy. Also, I've not taken at all into account the heterogeneity of the tissue and the shape of the tumor. That was something very simple, that was spherical. I've not taken into account the motion of the defects. For example, this morning, David Nelson shown plus or minus 1/2 defects moving. So here also they move, but this is very slow. I'm not sure that this is relevant in this context. Basically, they move at 1 micrometer per hour, and the size of the cells is of the order of 20 micrometers. So on the scale of 100 seconds, probably that's not relevant. Also, at some point, of course, it should be good to talk with people who know, but I think it's still very too early. I mean, so I will stop there, and it's not essential if I forgot to speak about the other protocols. So thank you very much.